Yeah. Sorry. In the next, at least I will try it. I have, yeah, probably it will not be a problem. Of course, what is also important for you to know, we have, I have recorded the complete lecture and also the exercises, which are very similar to what we did here 2 years ago. And also we have, let's say, from last year and from 2 years ago, all of the handwritten remarks. So it's there. I will have a look to have it work. Yes. Okay, but there's one important point. We have to agree on a date. Friday? Same time? Or is it too hard in the sorry? Okay. Same time? Friday? Let's have a look what in the Monday is not possible because I have appointment all day long. Let me have a look. Yes, no, on Monday is not possible because I have to hold exams in the afternoon, and in the before noon I have other appointments. Or Tuesday. Yes, who would be against Tuesday? Nobody against Tuesday, so we would say what, 10 o'clock? Okay. Yes, okay. Someone sent me an email writing Tuesday 10, please. Okay, so it's time to start now. What we have started in the last on the last Friday, it was thermal and mechanical engineering of assembly and packaging, and what you can see here is a design flow for power electronic modules. In fact, I would not say I developed that, but it was the design flow we adopted quite some time ago when we developed the electronic part of an electro vehicle. In fact, it was a smart car, and at that time we were also under considerable time pressure, because we had only maybe a year or so for the complete design, because that was some competition. There was another competitor who also did the design, and finally it was chosen which one to take. So we had to be fast, and so that we had to take the most advanced tools in order to be fast and in order to submit our offer in time. So that whole thing is, of course, based on a CAD draft or also CAD construction, but in fact, it not only means the mechanical part. It also means the schematic, the electronic part. And in that way, so it's not one draft, but it's several drafts. The first thing we wanted to do was to do the thermal management, because we knew that due to the high power dissipation, which was a few kilowatt, we should be able to dissipate that heat. That means to have a low thermal resistance in order not to overheat the semiconductors. And at that time, the maximum operating temperature was 125 degrees centigrade. Later on, it was increased to 150 degrees centigrade. And in the meantime, you can find quite a number of power semiconductors operating up to 175 degrees centigrade. So at that time, 125 was the limit. And in fact, the whole thing was to make a design in which the temperature would come very close to 125, but not to exceed 125. The first thing was the electrical simulation. So here you can see the dissipation in over time for the semiconductor and for the IGBT and the diode. I think the second here is not correct, but it's fractions of seconds, because here the frequency is more or less proportional to the rotations per minute or rotations per second of the motor. Yes, it's an asynchronous motor, and so if you have, let's say, 60 revolutions per second, then the frequency to drive that is a multiple of that. So in that way, for the electrical simulation, several cases were regarded, and these cases were, for instance, drive at full throttle, start up on a steep slope. So in that case, the motor, the RPMs are almost zero, but you have a very high current. Or in the other, and that could be that case here, and or so-called recuperation. That means your kinetic energy is transferred back into the battery, and to that purpose, the current must flow into the opposite direction. And that are cases, and these cases must be taken as, that's the worst cases, and these must be taken as the examples on which the whole design base. So that's very important. And to that purpose, we have the electrical simulation. In the meantime, there is already a standardized drive cycle for electro vehicles, which is a base for such designs. So, but at that time when we did it, we had to find it on our own. What would be the electrical behavior? That means what are currents, what are voltages in every semiconductor over time. And based on that, we can have a semiconductor model, and we can do the simulation of the power dissipation. So that was not my business. That was the business of the electrical engineers in that project. On the other hand, all that had to do with assembly and packaging, that was my business. Here for that part, I was a project leader, and here two aspects are important. How is the whole system built up? For instance, which kind of substrates do we use? How do we connect all of the parts together in former times, for instance, power modules were just screwed onto a heat sink, maybe having some thermal interface material in between, but here we did something different. We soldered it all together. And the lowest part here is the cooler. That means that is, let's say, a flat device through which water is flowing and on which all of the electronics are assembled. And in winter, for instance, even the cooling, the heat that is cooled away can be used for heating the passenger compartment, for instance. So that is, we had to perform computational fluid dynamics. That means to compute what can be dissipated, and then based on these informations, thermal management and temperature distribution were calculated, and the result was quite interesting. The initial design by our electrical designers, it had, which was based on a standards design and on standard modules that can be purchased, that used 9 modules in parallel. And after we were finished and we had optimized it with respect to thermal resistance, we only had to use 6 modules. So that means 1/3 of the effort for building it, for the semiconductors, for the substrates, all was reduced by 33%, and that's quite a lot. And in that way, we did it. Later on, we also developed, let's say, a model for reliability of that thing, but I must say that is not yet finished. We are still doing some research in that field of reliability. Okay, so that's the point. But in many cases, especially if you do not have so advanced tools like finite element or computational fluid dynamics, you can try with an easier method. And one of the methods is just the idea of thermal resistance. Thermal resistance means it defines how many degrees the temperature rises in the hottest point in a device when you dissipate 1 watt in that device. And of course, that depends on the design. It also depends on the material. If you have more copper in it or more aluminum nitride or what else, what's the best material with respect to heat dissipation? Diamond. Diamond is, it can be 5 times better than even silver or copper is. So that's really good. And at the same time, it's an insulator. But of course, making substrates of diamond would be a little too expensive. So diamond is rarely used. Okay, so here we have several to even 100 Kelvin per watt. So that's low power. And also we must say, we can define it as junction to ambient. That means ambient is the medium which does the cooling. For instance, the air here having what now is 26 degrees or so, and junction is where the hottest point in the semiconductor is. Initially, the junction in a bipolar transistor is the PN transition point, yes, and there most of the heat is dissipated, but we just call it junction to ambient when we mean the hottest place in that semiconductor. Okay, in other cases, especially when it's designs which are made for higher power, and when we want to disregard the effect of the surrounding, then we give RTH junction to case. So that's defining more the thermal resistance inside the package, and not as junction ambient, the overall thermal resistance from inside to environment. Okay, so that is important. We have also seen on that example that that two phenomena are very important for low thermal resistance. One is the material. Of course, the better the thermal conductivity is of the material of the housing, the lower the temperature and the lower the thermal resistance will be. On the other hand, if we have an air cooling, the faster we blow, the lower will be the temperature and the thermal resistance. But of course, both resistances, junction to case and case to ambient, are in a series. And even if we bring that case to ambient to 0, even in that case, the junction to case resistance would remain. It's not even that. Both resistances in reality are not really independent. In fact, we find when we reduce the case to ambient resistance, then typically the junction case will increase. That is because, in fact, it's not just a linear problem, but it's a 3D problem. Okay. Then the question was for heat transfer mechanisms. The first mechanism is just heat conduction. So here we have so-called Fourier equation, which says the heat flux, which is the power going through a certain area, is proportional to minus the temperature, the heat conductivity multiplied with the gradient of temperature. And in that way, at least for such a brick-like element, we can compute first of all the heat flow, but later on we also have to compute the thermal resistance. And on the other hand, the heat flow, when we have cooling against the wall, it is we define a heat transfer coefficient, which is the heat per area and per temperature difference between the medium and the hot material or the hot plate, for instance. Okay, so typical values between 1 and 10 for free convection of air. Free convection means we do not blow artificially, but it's just, yes, why do we have free convection? What's the reason? Yeah, but that was not a reason. You said we have convection because hot air goes up, but my question is, why does it go up? Yeah. No, it's not wrong that it has more energy. No, it expands. Boyle-Mariotte's law. And when it expands, we have the same mass in a larger volume. That means density goes down. And so what has lower density will go up, because then we would create a pressure difference, yeah, between upper and lower, and that's a reason. Okay, so convection is the main reason why we have weather and why we have climate on Earth. Okay, then we have forced convection. So maybe the heat transfer coefficient can go up to 100 watt per square meter and Kelvin. But what is much better is, of course, water cooling. And here values between, let's say, 500 and 10,000 are typical, but these are defined mainly by the characteristics of the flow. So for instance, it depends much on the Reynolds number of the flow we have here. Okay, then we have radiation. The heat flux is proportional to the temperature to the power of 4 of the heated part that radiates. But we could say maybe up to 150 degrees centigrade or so radiation is not really important for cooling. But it is important, we will see it. And then we can have phase transition like boiling, for instance, that is inside a heat pipe. Thermal conduction, we can say we have derived that if we have such an element, the thermal resistance is proportional to the length in the direction of the heat flow divided by the area and divided by the heat conductivity. And that means, of course, larger areas are bigger, but one of the severe problems is that heat always is dissipated first in a very small volume, yes, and in that way it must be distributed from a small volume to a large volume. And only when it's in a large volume, we also have a large area from which it flows. And that means to come to a large area, when we have a point source, we also need to have a large distance. And that's the reason why concentrated heat sources are always making problems, yes, because you first have to distribute the heat until you can spread it efficiently. And to that purpose, for such point-wise sources or sources in small volumes, you also need materials with a high heat conductivity. And fortunately, silicon is quite good at conducting heat. Also, silicon carbide is very good. Diamond is much better, so that's one of the reasons why engineers are working on developing power semiconductors on diamond. No, imagine you have a small source of heat, yeah, and the area around that is small, yes. So when you want to come to a larger area from which you dissipate it, you have to increase the D, yeah, and that means to spread heat, you can only overcome that by having a very good conducting material. Yeah. Yeah, but because you always must think it that way, yeah, and then it comes always to a somewhat larger brick, yeah, and that always means if you take such a simple model, you have an area, and the area has a certain, let's say, edge lengths, but at the same time, the thickness length is similar like the edge length. Yeah, and that means heat spreading always needs a certain length, and in that way, when you have that length, the d is large. In fact, it's not the simple formula, but you would have to make in that case, you would have to make an integration over a ball. Yes. Here we have some properties. We also must keep in mind the temperature conductivity. The heat conductivity is not related to the mass, but it's related to the volume. On the other hand, the Cp, which is the heat capacity of the material, it's typically related to the mass. So when we also take into account heat capacity, we also must know the density of that material. So that means how many kilos we have per liter of that, or cubic decimeter of that material. As I pointed out, we have quite a range. Tin and lead are in the range of 30 to 60. And again, here we find a large scatter of the values in literature. A typical value, I would assume also for the exam, is something like 50 would be okay. Silver goes to 400, but that is only, but that is not for sintered silver. Sintered silver is worse because it's not completely sintered, and to that purpose it's lower. It's somewhere between 200 and 400. Lead alloys here, it gives 25. Tin alloys are typically better, 50. Here we have copper has around 400 when it's pure copper. When we have a lead frame, it's maybe 250 or so, because it's an alloyed copper. Alumina goes between 20 and 30, and aluminum nitride is, here we have given 180 at 20 degrees centigrade, 110 at 300, and that's a rule. All ceramics, they degrade in, or they have a lower temperature, thermal conductivity at higher temperatures. And that means when we make a design, we always must take the material data of the high temperature, not of the low temperature, yes, because then at high temperature, we must dissipate that heat. And, but anyway, aluminum nitride, it's maybe 150 or so at 200 degrees centigrade. Why do we need the Cp, the heat capacitance of the material? Why do we need it? Up to now in that lecture, we didn't have something that had to do with Cp value, but why would we need it? Yes, so yeah, maybe we can say it a little shorter. It's affecting how fast we heat something. So if we have a low heat capacitance, we also need little heat to bring it to a certain temperature. If it has a higher heat capacitance, we need more energy. And the cooling rate and heating rate are in temperature transitions are depending for one, of course, on the power, and for second, on the heat capacitance. And that, and the third thing is, of course, the thermal resistance. So you could say it's similar like an RC element in electrical engineering. So we have the thermal resistance and the thermal capacitance to take into account. Yes, when we have thermal networks, the most simple thing is we assume all are in a series. So junction to case, case to ambient, both in a series. As I pointed out, that's a simplification. That simplification is roughly valid. Let me say it that way. On the other hand, we also have cases where we have thermal resistances in parallel. For instance, sometimes we have cooling of the semiconductor in both directions, so heat going down and heat going up. And in that case, we have resistors in parallel, yeah. And in that case, of course, it's just the inverse law of parallel resistors. It's like in electrical engineering. So here is an example. That example is quite old. I took it from a textbook. The example, it's a ceramic housing. It has pins here, so it's some kind of pin grid array or so. And in that housing, here we have something like a, I don't know, HTCC or LTCC, and on that we have the chip in a flip chip mounting, and on top of that is a cap. And we do not just want the heat to go through the flip chips, but and to the bottom, but we also want the heat to come to the top here. So normally, reasonable people would put on again some pin fin cooler on top, and because you never know the precise distance here from the chip top to that cap, of course, there must be thermal grease. So in that case, I would say that thermal grease is, that image shows it much too thick. Yes, so here I would say that thermal grease would rather be a heat insulating material if it's so thick, but it should symbolize the material is not really good, but it's better than having nothing. And so in that way, we can say the heat goes in the following way. Here is the heat source at that point. The heat goes through the flip chip, goes through the body of the package, goes through the pin. Then it goes from the pin into the card. And so here you could say that's an isothermal layer, because to the right or to the left, again, we have such modules. And from that card, it can go via convection to the air, which is flowing around that card. On the other hand, we have also the possibility that the heat goes up and then it distributes in the cap that has a certain thermal resistance, and also it can go up into the air. And at the same time, also we have one path around here coming to that point here. So that means, and that point here should be that point here. So that's an example. And then in the next thing, you can estimate the individual resistors. And in fact, I think the method is not so bad, because you just estimate these resistors. And maybe here we have 2, 4, 5, 6 resistors. Normally, I would take more. Let's assume we have 10 resistors to model it. Yeah, and every resistor is estimated. And as it's an estimation, you are wrong by a factor of 2. Yeah. So instead of 10, let's say you have 10 resistors. Each should have 1, but or each should have 10, and then the total is 100. And then one of these is not 10 but 20. Yeah, that means 50% mistake you make in one resistor, but the whole total, then it's not 100 but 110. And that means you have 10% error, which is not so much. And that means, and the next thing is, as long as you do not make systematic mistakes, even these mistakes you make can cancel out. And that's a reason why that method is quite good. Just if you have sufficient of resistors, you model, or you estimate, the errors more or less cancel out. As long, and that's important, you do not make a systematic mistake. And one of the things which are always crucial is, on both paths here, we have the transition to the air. Yes. And of course, if you make a severe error here, that has a big effect on the total behavior. So that means especially high resistances have a strong effect on the whole thing. And in the end, the method is quite good. What you also can do is, if you have these individual resistors you take into account, you can also estimate what their mass is. And when you know their mass and the material, you can estimate their thermal capacitance. And in that way, you could also do a model like the Foster model, which gives you for each element here a thermal capacitor. Let me say the Foster model is physically not correct, but it works, and in that way you can also model heating effects. The correct model is Kauer model, where from each point you go to ground with such a capacitance. Yeah. Not so beautiful. I put it away. But that's not part of that lecture here. It's just for your information. Okay, as I said, the thermal resistance then is estimated. You have the thickness of the layer in the direction of the flow. You have the area perpendicular to that, and you have the and you have it for that individual layer. And in that way, you can do it in a series, or you can do it for the parallel ones. When you do such a calculation, having it with that formula, that would mean the following. You have a small volume, and from then you come to a larger volume. Yeah. So let's say a small brick and a big brick. But it is clear that the heat is not uniformly distributed in the big brick, because it has to spread. Yeah. And there are two, yeah, let me say it that way. You have that layer, and you have that doesn't look so beautiful, but okay. So the heat here coming here in here, it must spread. And that means, of course, here in the middle, it will be hotter than on the corners. And in order to account for that heat spreading, we can also have some factors, some spreading factors, which can be used. When you are in the exam, you disregard these spreading factors. You can all just assume the heat would spread ideally. Yeah. In fact, it doesn't. There was an American engineer, his name was Kennedy. He did some calculations how heat spreading is, so that can be accomplished quite easily, let me say it that way. But nobody does it that way anymore, because nowadays everybody uses finite element, and in that way it's inherently in the simulation. As I said, heat transfer with radiation, I already said. We have the heat flux, but we can also say the total dissipated power from a body with the surface of A is proportional to the temperature of that body to the power of 4 minus the temperature of the surrounding to the power of 4. E is the emission coefficient. That's a value between 0 and 1. How do we call a body with an emission factor of 1? At the same time, it also has an absorption factor of 1. Black body, yes, that's correct. And so if we have something like a mirror surface, of course, that has a low emission factor, that could be, for instance, if it's highly polished silver, only 0.01 or 1%, yes. On the other hand, if we have something done black and not in a glossy black, but a dull black, then it can be almost 1. And the sigma here is the Stefan Boltzmann constant, which we also know. And in that way, we can calculate what the emission is. Let me say, in normal applications of electronics, we do not regard the radiation as a real cooling factor. Where it is, for instance, a very good cooling phenomenon is in a light bulb. Yes, it has that filament glowing at 2,500 degrees centigrade, and all of the heat that is dissipated is radiated away. Yeah, unfortunately, it's much. A light bulb has only, I don't know, 10% of efficiency with respect to light efficiency. On the other hand, LED has more than 50% efficiency, even 60 or so, or 70, but the rest of the 30 is not radiated at high temperature, but it is as low temperature, and so you cannot get rid of that heat by radiation, but you must get rid of it by normal electronics cooling. That means by heat conduction and by convection. And that's the reason, of course, why also a light bulb is so cheap. Yes, you do not need anything for cooling. Yes, it's just a wire hanging on two strands. Yes, and in that way, yes, of course, a light bulb itself, it's hot. Yes, if it's operated, maybe it's 120 or so degrees centigrade. You burn your fingers, but it's not really a problem. Yeah, because all of the heat heats the room by radiation. The thermal resistance is then 1 divided by 4 sigma divided by the surface area and divided by the temperature to the power of 3 in case we have radiation. So for instance, what you could do here is compute the thermal resistance, for instance, of your stove in your kitchen, because you know it has a certain temperature, it has an area, and in that way you can compute that. So here are several values. I already mentioned it. It can be between a few percent in the for polished noble metals. Aluminum is worse because it always has a little oxide on it. That means when the aluminum oxide is thicker, like in anodized aluminum, then it almost is a black body. And so we are not really sure what the emission coefficient is. And again, that makes calculations quite unprecise. Normally, let's say for cooling, radiation is not so important, but it's important for knowing the temperature in electronics. That is just an example. As you can see here, that's a power device. That image was already taken quite some time ago, but it's still valid. Here you see the semiconductor has 160 degrees centigrade on the top, while we see almost nothing in the case where it is turned off. Here you see the E, that's the emission coefficient, is assumed to be 0.78. That must be calibrated before. There are several methods. One is to put on a special dark paint. And that paint has a well-defined emission factor. If you don't have that paint, you have a problem, as on a semiconductor, you have different locations, and each location has a different emission factor. And one of the effects is that even if the temperature is uniform, it appears we have hot spots, but in fact, that's not hotter, but that's material have just a higher emission coefficient. You can also do that before operating the semiconductor. You put it on a hot plate. You determine the emission factor for every pixel, and later on you use that emission factor for every pixel. Of course, you must not move the image in between. That's one possibility. In that way, you can already have thermal cameras quite cheap for under 1,000 euro. But if you pay really a lot of money, you have a thermal camera that takes up for the pixels the spectrum of the radiation, and from the spectrum of the radiation, you can calculate precisely the temperature and the emission factor. So that spectrum in German, it's Wien's Verschiebungsgesetz, Wien's law, and that gives us the distribution of emission as a function of the wavelengths. And cameras doing this are much more expensive. So here we are talking rather about 50,000 euro or so. But that was a simple camera. We have also done some investigations. For instance, what is doing much better is so-called lock-in thermography. So we have some harmonic heating and cooling, and by measuring in phase, we can suppress much of the noise. Yes, you probably know what lock-in technique is, I would expect. And so in that way, so we had a master thesis doing that. And if you have some harmonic going in and some harmonic going out, you can have a phase shift. And from that phase shift, for each pixel, you can again make an image. And so you get the so-called phase image, not the temperature image. And the phase image can show you clearly if there is, for instance, a damage in temperature cycling also. So that's very interesting. And so one of my PhD students and one of my master students, they developed that method. Okay, now a last word about convective cooling. So we have already seen some values. That's typically the surface heat flux we can have, that is in watt per square meter, and the temperature difference. Of course, taking temperature difference divided by the surface heat flux is just, or the slope here is just the thermal resistance we have. And so we can see direct air, natural convection, forced convection, immersion. Here it was immersion in fluorocarbon. That was done for the first supercomputers. They were just in a certain organic liquid. And so there was convection, not by air, by that organic liquid. But that was a very expensive solution. Now, for immersion, we can also use boiling. That is a so-called heat pipe. So some material is boiling and you can have the maximum heat transfer when you have boiling. That's much better than heat conduction. That's also the reason why we have a steam engine or steam turbine and so on. It can be even better than forced water cooling, but boiling has one disadvantage. The disadvantage is when the heat flow is too high, the boiling mechanism is just breaking down. You could imagine it that way. If all of the medium is evaporated, there is no more left for further cooling. And that means boiling, if it's too strong, your cooling mechanism will break down. But boiling typically is used in your laptop because the laptop typically has a heat pipe. So some medium is boiling on top of your processor. It is, let's say, forced away by the pressure it develops. it's cooling on some surface, and then by wicking, that means by surface tension, it's brought back to the processor surface. Okay, we also had these values, so one thing that is also important, because we often need it, that's a pressure contact. Again, here we can see the heat that is transferred is proportional to the area. It's proportional to the temperature difference over that contact, and proportional to the heat transfer coefficient. If we bring two surfaces of solids into contact, they do not touch completely, but they are only, as for my fingers, local points where we have that contact. And the result is the heat transfer over that interface is much worse than the heat transfer inside the material. Yeah. If you have your kitchen stove and you have a pot and you have it just starting to boil, you can hear it. And when you press the pot, you can notice immediately the boiling sound will be stronger. It's interesting. And the reason is you have immediately more heat transferred. The reason is the more you press, the lower the higher the heat transfer coefficient will be, because the area you press together is larger. Again, here we have that heat transfer coefficient. It is depending on the surfaces you have and on their quality. It is somewhere between 2000, which is really bad, and up to 100,000. So my idea is if you take such a value and you assume something, that maybe you take 10,000 or so as a reasonable value. When you have thermal grease, so let's say that is the surface you have, then you only have heat transfer in that way. But when you put in a thermal grease, that will also contribute to heat transfer, not only the solid. But that also means when you would have a thicker layer of the thermal grease, yeah, in that way, then the result would be it's more a thermal insulator. Yeah, so the trick with the thermal grease is that it should just fill the gap you have anyway, and it should not increase the gap. Yes, so you can have a certain improvement. I once forgot it in my PC processor to put in the thermal grease, and after a very short time, the processor reset itself due to overheating. Okay. Now let's look at the result of heat. And one of the results is thermal expansion. And generally, the stress is something like the effective Young's modulus, like the delta alpha times delta T. Yeah, that is a basic formula. If you are in the exam, do not use it because it's too simple. Yeah, it's just if you would use it, you would have to use the proper effective Young's modulus, and that is depending on the geometry. For instance, you could have a model that says one of the effective Young's modulus is 1 of E1 so that's like this formula. You have the delta alpha. The dt is by the integration over temperature here. And the effective Young's modulus in that two-layer system would be just calculated from the inverse rule of mixtures. That could be an example. Also, we have already derived it in an exercise where the chip is between two layers of molding compound, or where the lead frame is between two layers of molding compound, and then the effective Young's modulus is something like 1 divided by E is 1 divided by E1 plus 1 divided by E2. And in that way, we can get that formula. Yes. So again, we have that formula here. What is important is always from which temperature on do we calculate the stress. Of course, we could assume that at room temperature, the whole thing would be stress-free. Yeah, it's cold, so it's stress-free, but that's not, in most cases, it's not correct. The relevant thing is the stress-free temperature, and in some assembly processes, for instance, in gluing, we have a hardening temperature. And then we could assume the hardening temperature is the stress-free temperature. Yeah? So it's hardening, and the stress develops because we cool it down from the hardening temperature. If there is a glass transition temperature that is lower than the hardening temperature, then we take the glass transition temperature as a stress-free temperature. But if we have a material that has a high glass transition temperature, but it is hardened at a low temperature, then we could say it is the hardening temperature. In solders, we typically take the soldering temperature as, or the, let's say, the solidus temperature of the solder as the stress-free temperature. So we can take hardening. We can take solidus, or we can take a glass transition. And that must be reasonably taken for stress-free temperature. One of my PhD students, he did a very thorough investigation, and we had several effects, and we were playing around with materials properties and selecting the right deformation model. Is it plasticity, creep, and so on. In the end, the best result he found after he selected the proper and correct stress-free temperature. So that's really important then. Another thing that is important when we look at stress phenomena, up to now we have regarded two materials operating against each other, but that's normally not the case. For instance, we have a chip, a solder, a substrate. Solder can also mean adhesive, it can also mean sinter layer or such a thing. So if we cool down, and both would cool down more or less independently, that is when the solder is really soft, or when the adhesive is soft. Both of operate more or less independently. And so the solder or the adhesive will take up all of the strain difference here. Yeah, that means the stresses in chip and substrate are not so high, but the deformation in the solder is much. And that means the solder can crack. On the other hand, if we have a harder solder or we have a sintered layer and more soft substrates or thinner substrates, then the whole thing will be coupled very strongly, but in that way it has a bimetal effect. The strongest effect, of course, would be if there would be no solder material at all, if it would be directly coupled. And in that way, these are the two cases which are relevant. Also, that case to the right explains to us why a solder will fail. On the other hand, the left case will rather explain why the chip will crack or why the substrate will crack. Why is it more probable that the chip will crack than that the substrate will crack in that case here? Do you have an idea? Yeah, you said outward bending, but what it means is the surface of the chip is in tensile stress, and brittle materials always break under tension. They do not fail normally under compression. So when I break that rod here and I overbend it, it will crack on the top, not on the bottom here. Yeah, so that's due to it's a brittle material, and brittles fail by tension mostly. It's an important rule, and that means the chip would crack here from the side or from the top. Okay. Again, we can see it here. The chip, if it's really normal stresses, it is from top, but we know from mechanics, when we have a gradient of normal stresses, that's equivalent to shear stresses. Yeah, and shear stresses also can lead to cracks coming from the side here. And now, again, we can have a look what will make the situation worse. The situation will be worse when the stress in the chip is higher, and especially when the stress in the chip surface is highest. Now, let's take a situation where the chip is relatively thick. We do not treat a situation where we have an extremely thin chip, but a relatively thick chip which can lead to high bending forces. Yeah, if the chip is very thin, it cannot bend back. Yeah, the thinner this is, the lower is the force I need for bending. And in that way, we regard a situation where a chip is relatively thick, like in MEMS, for instance. And there are several influences on the stress. So let's say we have an effective Young's modulus, but the Young's modulus of silicon is constant. So that you could say that is no longer regarded, but you can have different substrates. And of course, you can expect when the substrate is stiffer, then also the stresses in the chip will be higher. That seems reasonable to me. Also, you could say, as a rule, generally, if you have bigger parts normally in assembly and packaging, you have a bigger stress problem, or stresses are often bigger in bigger parts. So the length of the chip could have an influence, and we could expect that longer chip edge leads to higher stresses. And then we didn't regard something here, but we regarded it previously. That's the Young's modulus of the solder. So is it soft or is it hard? Or you could say, is it stiff or is it compliant? And and when is the solder compliant? That is when it has a low Young's modulus, but also what makes that solder joint also compliant? So it can deform more. It's the thickness, yeah, of that. Because shear stress is just defined, shear strain is just defined by displacement divided by the thickness of the sheared layer. Yeah? So in that way, we could say the thickness of the die attachment material has an effect. And there is one formula I found in literature that is maybe not the very most precise formula, but it describes the situation very well. So you could say, of course, the stress in the chip is something like proportional to delta alpha. It is also proportional to delta T. And it is proportional to the effective Young's modulus. And that is the Young's modulus of the substrate. That is of the mounting material. You could also say the die attachment. The length is the length of the chip, and the X is the thickness of that layer here. According to that formula, you can say when the chip is larger, you also must make a larger thickness of the die attachment. We have seen that in the example of the silver glass die attachment. And there is a geometry factor. Normally we take 1 for that factor only for hard ceramic materials. So for instance, mounting on aluminum nitride or mounting on alumina, and having a hard die attachment system like solder or so, then we can take a value of 0.1. Also, again, that's not so precise, but in the end, this formula is important because it shows us what the most important factors for stress development are. It's not the most precise formula, but for learning and for seeing what effects are, it's very efficient. So therefore, I like it very much. There was another guy, his name was Suhir. He did it analytically. I will not go into the details. He could do it for a multi-layer system where you can compute it much more precisely. You get a recursive set of formulas to compute that. For people interested in such topics, you can have a look at that. But the most interesting thing is, again, you see delta alpha, delta T, and some factor, and all of that factor is nothing but the effective Young's modulus in that system. Of course, when you look at the individual layers, you can also compute the stress. You have to take into account an individual effective Young's modulus for that layer. But in the end, E effective times delta alpha delta t is always correct. Or you take the integral form if the properties are temperature dependent. And the art is just to find out what is effective Young's modulus. Okay. That is to determine stresses. The second problem is to determine what happens to the solder or die attach material. So that is a much more complex question. And that here is, for instance, from a finite element simulation one of my PhD students did. So we have a substrate, we have a ball grid array, we have the balls. And when that whole system deforms, in that case, it would happen that the deformation behavior is quite complex. And in the end, in that case, it leads to the fact that these solder joints are sheared and these are more pulled, while these here on the corners are more compressed. There are other cases or situations, for instance, when we have shear on the outside, but also pull, which is even worse. What is also important is to know which of the solder joints will fail. Which one would you expect that will fail? So the left is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which one will fail? 1 or 10? Yes, 3 and 7 are also in danger because 3, 4, 5, 6, 7, no, 8. Because here the behavior of that BGA is completely different. So we know that from many experimental investigations, the corner balls will fail first. So that's the reason when you have 354 balls, never use the corner balls. You always have sufficient of IOs, and so you don't use these because they will fail earlier than others. What will also fail here is these 3 and 8. Unfortunately, they are close to the chip, so normally we like to use them in a design. But in the end, the question is, how can we predict the behavior of such solder joint to fail? Here, that was another PhD work in my lab, and that was Mr. Pustan. And together with Mr. Zhang, he did his master thesis on that topic. They had many BGA, and these BGA were taken at different cycle numbers. It was always cycling -40 to 150. And here you can find, for instance, 0 cycles that looks fine, on top solder mask defined, on bottom non-solder mask defined. So 250, it doesn't look smooth anymore because we have some internal deformation, and that leads to so-called surface kinks. These kinks here accumulate, you see it already here, to cracks, mostly near interfaces, and then these cracks grow. grow, and here at 1,500 cycles, the crack is completely through. So what's the number of cycles to failure? It is when the crack has gone through that ball, and that means, as it in most cases comes from both sides, somehow also the radius of that ball is relevant. Okay, but we also see on the underside, also here, cracking already starts. What is also interesting is to know the material itself, it also changes. Yes, between 500 and 750, we see, yes, the structure becomes much more coarse compared to the initial structure. That is something, if you have engineered parts from mechanics, they will never change their internal structure. They stay as they are, but solder joints don't. So now let's make a simple model that's for finishing today. Imagine we have, to make it easier, we just take a chip resistor that is, for instance, alumina or so. For example, that also can be barium titanate in a capacitor. So on the side here we have the solder joint, and we have a length, and that length defines not the length of the device, but it decides the distance from the outermost solder joints. And so when the whole thing expands, we have for the device a CTE, and we have for the substrate we have a CTE, and we have for the component a CTE, and both expand. Of course, the expansion is something, delta L is proportional to the CTE, proportional to the delta T, and proportional to the initial length we regard, and that is both for the substrate and for the component. The difference in length is the length change, which is leading to stresses, because when both expand, but in the same manner, there will be no stress. Yeah, so moving like this will not lead to stress in between here, but moving like this will lead to a displacement and a stress. So we see the delta L is delta alpha delta T times the length of that here. Okay, what's the effect of that length change here? It leads to a shear strain. The reason is when we have shear forces, no, it's a little larger. It will lead to such deformation, and that is the delta L, and that is the height, and the shear strain is just the delta L divided by height. So it's what we already saw. If a die attachment or if a solder joint is thicker, the strain, the shear strain is lower. Okay, we can have that because it is a symmetric problem. We divide the strain by 2. So the delta L is distributed to both sides. And so we can say the shear strain is delta alpha delta T times the initial length divided by twice the height of that. If it's square components, then of course in square components, and we have joints here, then if that is the L, that is L times square root of 2, and then we have to multiply it with that factor. Okay, that's a shear strain. Normally, in isotropic materials, we can convert shear strains to normal strains or normal strains to shear strains. That is important because material properties normally are measured by tensile tests. Yeah? And in a tensile test, you have normal stress and normal strain. Yeah? So stress is force divided by cross-sectional area. Strain is length change divided by length. Yeah, so normal stress is normal strain, but here in that problem we have shear stresses and shear strain. So we must convert, and there is a simple rule that is only roughly valid in plastic materials, and that says the normal strain is square root of 3 larger than, no, the normal stress is square root of 3 larger than shear stress. And the normal strain is the shear strain divided by square root of 3. Also, we could say as a rule of thumb, the shear modulus is roughly the Young's modulus divided by 3. That's a crude approximation, but here we use it because it is relatively helpful. So in that way, we can take into account the relevant stresses and strains, which are shear stress and strain, and compare them to normal stresses and strains. Okay, I already had that. Of course, it's also important. The shear stress is shear modulus times shear strain. Normal stress is Young's modulus times elastic strain. Okay. Same here. Okay. What happens under much strain? That's an example. Again, Mr. Fix did his dissertation in Bosch under my supervision. And that's how a chip resistor looks after 1,500 cycles, minus 40, 125 degrees centigrade. So it looks not so reliable anymore. And having a cross section, we can see there are many cracks, there are holes, especially here under the chip where there is a small gap, a small height. We have a large shear strain. We have only cracks here, we can see. And also the structure changes significantly. Okay. But how can we predict here what happens? And to that purpose, there is a relationship which is really important, and that is the dependency between the delta epsilon. Epsilon is the strain range, and the number of cycles to failure. And when we have two cases, one is what will fail first, and you can say that depends on the deformation mode, and that can be elastic, and that can be plastic. And you can see here, these are the two boundary curves. And so that's the elastic range, and that's the plastic range. Unfortunately, it was written here, but that just means it's that curve here. So that's the plastic failure range, and that's the elastic failure range. Unfortunately, as we have seen, we have these cracks at 1000 cycles. It is that range here that is relevant for solder joints. And in that way, only this curve here is regarded, which is making the dependency between plastic strain and number of cycles to failure. And that can be modeled in a power law. And that says the number of cycles to failure is proportional to the strain range, to the plastic strain range, to the power of C2. But C2 is typically smaller than -1. So that could be -1 or -2, for instance. And that means when the strain range becomes larger, the number of cycles becomes lower. Again, that's what we already know. More strain is bad because we have more stress and strain, and more stress and strain means lower lifetime. Okay, that is the famous Manson-Coffin or Coffin-Manson law, and that is defining so-called low cycle fatigue. And now the trick is the following. We assume the strain we have calculated for that chip resistor. We put in the strain we have calculated. First of all, maybe let's take the data here that was from that dissertation. That's the number of cycles to failure. So 50% of all specimens have failed here. That's the number of cycles, and that's the Coffin-Manson curve. And you see there's a large scatter, but here we have a certain law that defines when, for instance, we have 1% of strain range, we have only, what is it, 600 or so cycles until the specimen fails. When we have 0.1% of strain range, that means 1 promille of strain, then it will live for 10,000. And now taking that formula, we can put in into our law this strain which we have derived. As we have seen, delta epsilon is delta gamma divided by square root of 3. And that is delta alpha, delta t times the length divided by 2 divided by square root of 3 and divided by h. Possibly also multiplied with square root of 2 if it's quadratic. And in that way, we get a complete formula, and that formula can be used for calculation of the lifetime. And again, here we can say, C1 is roughly 2. C2 is roughly minus 1.3. And in that way, we can calculate how many cycles it will be until our device fails by fatigue of, or low cycle fatigue of the solder joint. Okay, that's the basic relation. Also, please keep in mind that what I showed here is prepared in a way to make it evident and to show what the real dependencies are. If later on in professional life you have such a problem, you should not use my formulas here. They are only estimates, but do a more precise calculation based on, especially based on own measured data. Yeah, that's important. But for, let's say, for the basic understanding what happens in the low cycle fatigue of solder joints, it's a very good approach. So again, we see from these formulas what are the most relevant factors we have to influence it. And in that way, for instance, we can also have different designs. For instance, we can just take materials data and also maybe size of the devices we put in. And so we can make an estimate, for instance, which design would be better or worse. But the modern way is, as I was showing in that flow diagram, you should know what the heat dissipation is, you should know what the cooling is, you should go for the real temperature distribution. And based on the real temperature distribution, you can also make mechanical calculations. We can do such things as we have the hardware design using finite element method laboratory in the winter semester. And there such things are done using ANSYS, which is a much more precise method. On the other hand, again, also in ANSYS, results can never be better than the quality of the data you put into that simulation. Yeah. But in the end, here that's more the basic, what happens, what are the relevant factors. All modern engineers use finite elements method. And in that way, most of the design of assembly and packaging is done. Also, for instance, one of the companies who are very advanced at that is for instance, Bosch. Also, I'm always supervising some PhD candidates in that field of simulation of ball grid arrays and such problems. I have one just finished in Bosch and another one is just working in ZF company. And so it's a really important topic where there is still lots of research to be done. Okay, do you have questions? So, sorry? The acronym, I don't know. When you look at multi-physics finite element software code, ANSYS is one of the two most important programs. So it has been the most important. In the meantime, the COMSOL, which is initially based on MATLAB, has also become more important. So now in the IMTech, many use COMSOL also because it was, it had a better connection with MATLAB also, and it also was cheaper somehow. I'm always working with ANSYS because I started with it, and so also my staff, they only use normally ANSYS. It is very powerful because you can combine such things. You can do a current distribution. Based on that distribution, you get the heat distribution in the device, and based on the temperature distribution, you get stress distribution, for instance. And so that's so-called multiphysics. You can combine different physical domains, electrical, thermal, mechanical domain. Also, in the meantime, you can do something like you have a contact problem, so that is attached, you heat it, it's moving, so the complete design changes itself, yeah. And then, of course, when it moves, then heat flow is different, and such things can already be computed, and that is never possible doing it by hand, yes. So then otherwise you would have to do some iterative method by hand, and yeah, that's out of date, I would say. Okay, so that's how it is done, but here I tried to show you what are the most relevant reliability issues coming from assembly and packaging and degrading the lab. For this year,